Welcome to the third lecture on the Gromov-Hausdorff propinquity, titled The Modular Gromov-Hausdorff Propinquity. Our purpose is to present a distance on the non-commutative analogues of vector bundles endowed with a metric, in the spirit of the Gromov-Hausdorff propinquity on quantum compact metric spaces. Our construction is new even in the case of classical vector bundles with metric data. Our motivation is from mathematical physics, and our goal is to construct physical theories using metric approximations. Vector bundles and connections are of course essential tools in the formulation of quantum field theory, and thus, for our program to advance, the construction of a metric between vector bundles is a natural goal. We begin with a general review of metrics on vector bundles to motivate our work. A vector bundle E pi B over a compact Hausdorff space B with fibers modeled over C to the n is given by a locally compact space E and a continuous open surjection pi from E to B, such that for each x in B, first, the fiber E sub x, that is a pre-image of the singleton x by pi, is a vector space over C, and second, there exists an open neighborhood U of x in B and an homeomorphism R from U times C to the n onto the pre-image of U by pi, such that pi composed with R is the identity on B, and R at x dot is a linear isomorphism from C to the n onto the fiber E sub x for each x in B. Thus, a vector bundle is indeed a way to glue copies of C to the n over a compact Hausdorff space in a continuous fashion. The space E is called the total space of the vector bundle. Our purpose, however, is to work with vector bundles and not just their total spaces. A continuous section of a vector bundle E pi B over a compact Hausdorff space B is a continuous function psi from B to E, such that pi composed with psi is the identity of B. In other words, psi is a continuous function from B to E, such that psi at x is an element of the fiber E sub x. Of central relevance to our work is the space gamma of E of all continuous sections of the bundle E pi B. It is a vector space for the pointwise operations defined using the operations on the fibers. It is actually a module over the C-star algebra C of B of complex valued continuous functions over the compact Hausdorff space B. Indeed, let f be a complex valued continuous function over B, and let psi be a continuous section of our bundle. For each x in B, we set f times psi at x to be equal to f at x times psi at x, using the vector space structure on the fiber E sub x. It is easy to check that f times psi thus defined is a continuous section of our bundle. Thus, we have defined a left action of the C-star algebra C of B on the space of continuous sections of our bundle. With this action, the space of continuous sections of our bundle becomes a module over C of B. A natural question is, what modules over C of B are in fact modules of continuous sections for some bundles? To address this question, we need some notions of morphisms. First, a morphism of vector bundle is called a vector bundle map. A bundle map, GF, from a vector bundle E pi B to a vector bundle F rho C is an ordered pair of two continuous maps, the map F from B to C and the map G from E to F, such that rho composed with G is F composed with pi. Thus, in particular, G maps fibers to fibers. The ordered pair GF is a vector bundle map when G restricted to the fiber E sub x is linear from E sub x to the fiber F at f of x for all x in B. Second, a module morphism from a module M over a ring R to a module N over a ring Q is an ordered pair psi phi, where phi is a ring homomorphism from R to Q, and psi is a map from M to N, such that for all A in R and for all xi and xi prime in M, the image of xi plus xi prime by psi is phi at A times psi at xi plus psi at xi prime. If in particular R and Q are unital algebras over the complex numbers, then psi is linear as well. There is an obvious similarity between these two definitions, and it is not accidental. A very important theorem from algebraic topology is the Serre-Swan Theorem, which characterizes the modules of continuous sections of vector bundles over compact Hausdorff spaces. To state our theorem, we need two definitions. First, a module M over a ring R is finitely generated when there exist finitely many elements xi1 etc. xn of M, such that for any xi in M, there exist element lambda1 etc. lambda n in the ring R, such that xi is the sum lambda1 xi1 plus etc. plus lambda n xi n. Thus, a module is finitely generated when it is spanned as a module by a finite subset. Note, however, that unlike in the special case of modules over fields, which are then called vector spaces, there is no good notion of a basis for a module. Second, a module M over a ring R is projective when there exists a module P over the same ring R, such that M times P equipped with its product module structure is isomorphic as a module to a free module, that is, a module of the form R to the n for some natural number n. The notion of projectivity for modules may be phrased in terms of a natural lifting property within the category of modules over a ring, and it is thus a natural concept. The Serre-Swan theorem states that the module M over the C-star algebra C of B of complex valued continuous functions over a compact Hausdorff space B is isomorphic to the module of continuous sections of a vector bundle over B if and only if M is finitely generated and projective as a module over C of B. Moreover, the bundle provided by the Serre-Swan theorem for a given finitely generated projective module is unique up to a vector bundle isomorphism, that is, up to a vector bundle map with a vector bundle map inverse. Thus, finitely generated projective modules over unital C-star algebras are non-commutative analog of vector bundles over compact Hausdorff spaces. Moreover, the Serre-Swan theorem states that classifying vector bundles is equivalent to classifying finitely generated projective modules, and this is, of course, the root of the idea behind K-theory and its extension to C-star algebras. For our purpose, we look in a new direction, the idea of a metric on a non-commutative analog of a vector bundle. Metrics on bundles have a somewhat different meaning from metrics on metric spaces, though, of course, there is a deep relation. Informally, a metric on a vector bundle is a continuous assignment of a sesquilinear form on each fiber of the bundle. For this talk, we will only use positive definite sesquilinear form, that is, inner product, on each fiber. Formally, this idea translates to the following concept. a positive definite bundle metric on a vector bundle E pi B over a compact Hausdorff space B is a bundle map G from the product bundle E times B over B to the trivial line bundle B times C, such that for each point x in B, the map G, restricted to the fiber E sub x times E sub x, is an inner product. In particular, the product bundle in this definition is defined as a subset of the Cartesian product of E with itself, consisting of ordered pairs, whose coordinate images by the map pi are the same point in B. Also note that G is a bundle map but not a vector bundle map. While metrics on bundles can be defined with various signatures, for instance allowing Lorentzian metric, we will focus on positive definite metrics in this work. We now see how to translate a vector bundle metric to the module of its continuous sections. If xi and xi prime are two continuous sections of E, then we define the inner product of xi with xi prime as a function which maps any point x in B to the inner product of xi at x and xi prime at x using the form G at x. Note that this inner product takes values in the C-star algebra C of B. The resulting structure is called a Hilbert module. Let's define this notion. An inner product over M valued in A is a map from M times M to A such that, first, for all A in our C-star algebra and for all xi, xi prime, and xi second, the inner product of A xi plus xi prime with xi second is A times the inner product of xi with xi second plus the inner product of xi prime with xi second. Second, the inner product of xi prime with xi is the adjoint in the C-star algebra of the inner product of xi with xi prime. Third, the inner product of xi with itself is positive as an element of the C-star algebra. And fourth, the inner product of xi with itself is 0 if and only if xi is 0. Of course, the properties of an inner product on a module over a C-star algebra are motivated by the definition of a usual inner product over a complex vector space. In particular, we can use such inner products to define a norm on modules. Let A be a C-star algebra, and let M be a module over A endowed with some A-valued inner product. If we set, for all xi in the module M, the norm of xi as a square root of the norm of the inner product of xi with itself, then indeed we define a norm on the module M, and moreover, the norm of A times xi is less than the norm of A by the norm of xi for all A in our C-star algebra and for all xi in our module. In particular, the left multiplication by elements of the C-star algebra is continuous. A Hilbert module over a C-star algebra A is a module M endowed with an A-valued inner product such that M is complete for the norm induced by said inner product. It should be noted that not all properties of Hilbert spaces hold for Hilbert modules. For instance, not all module maps have an adjoint. Nonetheless, the theory of Hilbert module is rich and very important to C-star algebra theory, for instance, in its role in the study of induced representations and Morita equivalents by Rieffel. A first family of examples of Hilbert modules are free modules over C-star algebras endowed with the obvious inner product. In particular, C-star algebras are Hilbert modules over themselves. A second family of examples was given by the modules of continuous sections of a vector bundle equipped with a metric. Now, it turns out that there is more structure involved when working with metrics on vector bundles beside the associated inner product. There is also the crucial notion of a connection, maybe the most important concept in differential geometry. To discuss this matter, we briefly make an incursion in the world of differential geometry. Let B be a compact differentiable manifold. Let E pi B be a differentiable vector bundle over B, namely, E is a differentiable manifold and pi is infinitely differentiable. If G is a differentiable metric over E, then there exists a connection nabla from the smooth sections of the bundle E to the C of B module maps from the smooth sections of the tangent bundle to the smooth sections of E, such that for all tangent vector field X and for all smooth sections omega and psi of E, the Lie derivative along X of G at omega and psi is the sum of G at nabla along X of omega with psi and G at omega with nabla along X of psi. Such a connection is called a metric connection. When working with a tangent bundle endowed with a Riemannian metric, then there exists a unique torsion-free metric connection called the Levi-Civita connection. Crucial notions such as curvatures are defined using connections. We now bring all these ideas together. Let Mg be a Riemannian compact manifold, and let Vh be some vector bundle over M with a metric. Let gamma of V be the module of continuous sections of V over the sister algebra C of M, endowed with a C of M valued inner product induced by the metric H. As we saw, gamma of V is a Hilbert module over the sister algebra C of M. Moreover, the module gamma of T of M of continuous sections of the tangent bundle, that is, the module of continuous vector fields over M, is also a Hilbert module using the Riemannian metric G. Let now nabla be a metric connection over V. Thus, nabla applied to a differentiable section of V defines a linear map from gamma of T of M to gamma of V. As these modules have norms, we can take the norm of this linear function. This constructs a semi-norm on a dense subspace of the module of continuous sections of the bundle V. To make it into a norm, we take the maximum of this semi-norm with a Hilbert module norm. Our idea is to study the properties of this commutative prototype and then consider non-commutative analogues of this construction. We thus arrive at the following new notion. Let AL be a compact quantum metric space. A metrized quantum vector bundle is a Hilbert module M over A and a norm D on a dense subspace of M, which dominates the Hilbert norm on M, whose ball is compact in the Hilbert norm, and which satisfies some form of Leibniz inequality. Here, G and H are just real-valued functions of some real variables, and their exact form is actually a parameter of our theory. We call the norm D the D norm of the metrized quantum vector bundle. A full quantum isometry between metrized quantum vector bundles is a module isomorphism whose map between the sister algebras induce a full quantum isometries between the compact quantum metric spaces, and whose map between the modules is at once an isometry for the Hilbert norm and the D norm. We have seen examples of such structures. First, the construction we outlined using a metric connection to define a new norm on the Hilbert module of continuous sections of a vector bundle over a Riemannian compact manifold gives us an example of a metrized quantum vector bundle. Second, and quite in a different spirit, any free module over a quantum compact metric space gives an example of a metrized quantum vector bundle. We now turn to a truly non-commutative example, the Heisenberg module over the quantum 2 tori. We fix a real number theta, an integer p, and a natural number q. We also choose a non-zero natural number d, which is a multiple of q. We set f to be the difference of theta minus p over q, and we assume that f is not zero. Let f theta be the quantum torus for the deformation parameter theta, that is, the universal C-star algebra generated by two unitaries u and v, such that uv is exponential 2i pi theta vu. We are going to construct a module over the quantum torus A theta, which is known to be projective, finitely generated, and not free. This construction appeared in the work of Kohn and was then studied and generalized by Rieffel. We start with the Heisenberg group. All unitary irreducible representations of this group are known up to unitary equivalence, and beside the trivial ones, they are the Schrödinger representations. We pick the Schrödinger representation of the Heisenberg group where the so-called Planck constant is given by f. This representation acts on L2 of R, and we tensor it with a trivial representation on C to the d to get a representation of the Heisenberg group on the space L2 of R tensor C to the d. We then take a projective representation of the group Z mod QZ times itself on C to the d, using the rational P over Q. More formally, we have two unitaries W1 and W2 on C to the d, such that W1 times W2 is exponential 2i pi P over Q times W2 times W1. We then combine these two representations together into a representation of the quantum torus. Informally, the idea was to split the twisting by theta in two parts, a twisting by f and one by P over Q. It can then be checked that the space of Schwarz functions with value in C to the d is mapped to itself by this representation of the quantum torus restricted to polynomials in U and V. We then define an inner product with values in the quantum torus on the space of Schwarz functions. The completion of the space of C to the d valued Schwarz functions for the norm obtained from this quantum torus valued inner product is actually a module of the quantum torus A theta. It is called the Heisenberg module over A theta for the parameters theta, p, q, and d. Kohn introduced a natural object on Heisenberg modules, which behave like a connection. We work on the space of C to the d valued Schwarz functions, which is dense in all our Heisenberg modules. We define two operators on the space of Schwarz functions. Nabla 1 is a derivative, and Nabla 2 is a multiplication operator. We note that these two operators can be used to define a representation of the Heisenberg Lie algebra, mapping the canonical central element of the Lie algebra to the unit. The Schrödinger representation we work with is the associated integrated representation. Our candidate for a d-norm on the Heisenberg module is associated with a connection defined by sending an element xy in R square to the operator x times nabla 1 plus y times nabla 2. With quite a bit of effort, we then can obtain the following theorem. Fix a norm on R2. We define a norm on the dense subspace of the Heisenberg module over A theta for PQD as before, as a maximum of the Hilbert norm and a semi-norm obtained by acting with the Heisenberg group on the module. This semi-norm is reminiscent of the Lipschitz semi-norm, but in fact, for an element xi in the Schwarz space, it equals the norm of the map which sends xy in R square to our connection at xy applied to psi. Endowing the quantum tori with a natural matrix from the dual action of the two torus, and using the length function induced by our choice of a norm on R², the Heisenberg modules are indeed metrized quantum vector bundles. We thus have several interesting examples of metrized quantum vector bundles. We now wish to define a distance between metrized quantum vector bundles, inspired by our work on the Gromov-Hausdorff propinquity. The idea is thus to define a tunnel between metrized quantum vector bundles. Fix a metrized quantum vector bundle MdM over a quantum compact metric space A L of A. Fix another metrized quantum vector bundle NdN over a quantum compact metric space B L of B. Those are the spaces at the bottom, left, and right of our diagram. A tunnel consists first of a choice of a third metrized quantum vector bundle P D of P over a quantum compact metric space D L of D. That is the space at the top of our diagram. We then choose two module morphisms, one from P over D to M over A, called capital theta A, and one from P over D to N over B, called capital theta B, theta B. We then ask that both theta A and theta B be quantum isometries. Thus, the bottom part of our diagram is a tunnel between compact quantum metric spaces. We also require that the quotient of the denorm d sub p by capital theta A is d sub m, and similarly, we require that the quotient of d sub p by capital theta b is d sub n. In other words, we have a tunnel between A L of A and B L of B, with an additional but similar requirement regarding the relation between the module maps and the d-norms. The extent of such a modular tunnel is simply defined as the extent of the underlying tunnel between A L of A and B L of B. The modular propinquity between two metrized quantum vector bundles is then the infimum of the extent of all tunnels between these two bundles. We proved that the modular propinquity thus defined is a complete metric up to full quantum isometry on the class of metrized quantum vector bundles. Moreover, we were then able to prove, with some effort, that for fixed PQD, the family of Heisenberg modules over the quantum tori A theta is continuous in theta for the modular propinquity. We can summarize our work on the Heisenberg modules in one theorem, which we invite you to read. We include some references on non-commutative metric geometry for further readings.